Hello and welcome guys. Electrical Engineering 2017 optional paper. Circuit theory problems are here. Question number 1A of 2017 is for the circuit shown below. Find the current through the current through the 5 ohm resistor by using Thevenin's theorem and verify the same by using superposition theorem. Okay, so two parts are there. First, you need to find out the current from 5 ohm current through the 5 ohm resistor using Thevenin and verify the same using superposition. So let us start with the first part. Let us find out what is the current flowing through the 5 ohm resistor. So the first step is to remove 5 ohm out of the circuit. Okay, so keep this open. So this is the equivalent circuit. If you remove that, how it will be the equivalent, I'll show you. Look at here. We need to find out VA and VB. Okay, for that we need to understand what is the voltage in this branch. That is, what is the voltage at AD branch. Okay, so here I have written the second step is voltage across AD branch is VAD is equals to 100 volts. Now how this is coming, look at here in the diagram. This is A and that is D. Okay, so this is what the source connected here in the branch. So it doesn't matter what is connected in this branch. Okay, it is 40 and 6 ohm, so definitely it has to satisfy the KVL, and you cannot have two different potential across the same point. That means the voltage at AD branch must be equal to 100 volts. Okay, similarly, you can see in the BC branch, the voltage must be equal to 50 volts. Okay, so that is it. Now, you need to find out the voltage here. Okay, in this DC branch. So let us simplify this. First of all, draw the equivalent circuit. So equivalent circuit for the given problem, considering AD is 100 volts and BC is 50 volts, you will find something like this. So this is A, that's D point, which has been replaced by a 100 volt source, and BC is replaced by 50 volts. Then the branch DC I have written here as 20 volts for this power supply and 10 ohms. Now simply you apply the loop equation here. Okay, this is direction of current which I am considering, obviously because I need to go for AB voltage. Okay, so I have to consider this branch, otherwise I have to take negative sign. So let us write the loop equation. So that must be equal to VTH, which is VAB. So loop equation will come as, since this is negative sign, that is positive sign. So negative sign you are encountering first, hence minus 100. This is positive and that's negative. So VAB is VTH is plus VTH. Then this is plus and that's minus. So along the direction of current you are encountering plus sign for this E5 voltage source. Hence it is plus 50. Drop we are always taking as positive in this case. So plus 10 into I, and now this is negative sign and that's the positive sign for the battery here, hence minus 20, that is equals to 0. Now if you simplify this expression, you will find that the current, the voltage VTH is equals to 100 minus 50 plus 20, which is equals to 70 volt. Now please understand why I am writing current I is equals to 0, because your loop is open. So if the loop is open, you cannot have current there. And the RTH can be identified using this equivalent circuit. What you have to do for Thevenin is you need to short the voltage sources which are there. So if you short these three voltage sources, since this is the equivalent circuit, we can directly take from here. So if you short this, you will only left with the 10 ohms. Okay, so RTH is 10. Now you have VTH here 70 volts and you are having RTH both. Now you can easily identify what is the current which is flowing in this 5 ohm resistor. So let us see what is that. Then the Thevenin equivalent circuit for the given question will look like this. You are having this load resistance 5 ohms here, the Thevenin equivalent resistance that is 10, and the voltage source that is 70. Hence IAB can be identified as 70 divided by 15, that is 4.667 amperes. Now let us go for using the superposition theorem. So what we have to do, we have to consider each of the source acting alone, and then you have to find out the current flowing in this AB branch, and then you have to go for the algebraic sum of all the currents. So let us start with the even source. Considering this 100 ohm is only working, 100 volts is only working, and rest of the sources are not there. So you can easily see that this branch is in parallel with the 100. Okay, that means the voltage across this branch is already known to you, that is 100. Now the current can be easily identified by 100 divided by 15. Why 100 divided by 15? Because this 5 and 10 are in series with each other. Hence 100 by 15 will yield you 6.667. So mark it. This is equation number 1. Maybe you can call that. Now E2 is acting alone. So E2 acting alone, the equivalent model will look like this. So E1 is shorted, hence everything will vanish from this side. Okay, so this is also not there. You are having only this one E2 source and the associated resistance. Rest of the voltage sources are not there. Now you can see this is the zero resistive path, hence all the current must flow through this branch. If that is so, there is no current which is flowing in this 5 ohm as well as in 10 ohm resistor. Okay, so this is redundant now. So that means the current flowing in this 5 ohm because of E2, or only because of E2, is 0 in this case. Okay, so that is maybe equation number 2. Then 3, E3, E3 is acting alone. So look at here guys, rest of all the sources will yield for the short circuiting. Okay, because that voltages are in a single branch, hence they will short circuit and will finally yield with this equivalent model. And from here you can easily identify what is the current which is flowing in this AB branch in this direction. Okay, so A to B. So that is 20 divided by 15, which is 1.33 amperes. Okay, this is 1.33 amperes. Now E4 acting alone. So E4 acting alone is the same case as E2 acting alone. Look at here. So everything is short circuited. So because of this E4, all the current will pass through this loop. Okay, and there will not be any current in this branch as well as in this branch. Okay, so because of this you will find AB current is 0. Now E5 acting alone. So E5 acting alone, the equivalent model will look like this. And what will happen? E5 is 50. So these two are in parallel, and in parallel with this 10 and 15, so let us merge that, and you will find you can easily apply the Ohm's law here. Why this is so? Look at here, 50 by 15 will yield you the current. Okay, so this is the same case as we are having for our E1 problem. Okay, so this E1 and E5 are the same case here. Now because of that you will find this is minus 3.33a. So look at here, what are the currents which are available with you? One is 6.667 with a positive sign, the other is 1.33 amperes with a positive sign, and minus 3.33 amperes with a negative sign. So let us do the algebraic addition of these three and see whether we are able to get 4.667 or not. Okay, so if you go for the algebraic summation, you will find that you are getting 4.667 amperes. Hence, it has been verified that the current flowing through AB branch because of the rest of the sources, that is E1 to E5, is 4.667 amperes, and that we have verified using Thevenin as well as superposition theorem. Okay, now question number 3C is, consider the RLC circuit shown in the circuit below, where IS is 10 amperes, R is 2, L is 1 Henry, C is 0.5 microfarad, IL 0 minus is 0, that means the initial condition associated with the inductor is 0, and then determine V0 plus d by dt of V0 plus d2V by dt2 V0 plus after the switch is being closed. So look at here, when the switch is open, this is unenergized, so no energy here. This is also unenergized because that's not mentioned. Let us assume this is also unenergized. So when switch is open, the voltage across the capacitor is 0. Okay, and please remember, voltage across capacitor cannot change instantaneously, guys. This is a very important point. I repeat that, please make a note of it. Voltage across capacitor cannot change instantaneously. Hence, as soon as the T is closed here, the switch is closed at T is equals to 0 here, the current will start flowing, but the voltage across capacitor cannot change instantaneously. Hence, T0 plus voltage must be equal to 0. Okay, so that is fine now. So Vc at t is equals to 0 is 0. Now you have to go for d by dt of V0 plus. Now this is a very typical condition where you are having RLC circuit. So you will end up with a integral differential equation, IDE, integral differential equation. So the point is, if you want to find out d by dt of V0, okay, so generally you will see in book you will not find such kind of questions, because if you differentiate it once you will find d2v by dt2. Okay, then the problem is you will not get d by dt of vt at t is equals to 0. You will not get d by dt of vt, okay, at t is equals to 0. Hence what we have to do, you need to solve this expression and you need to find out the voltage value. So I am using the Laplace transform method. I am converting everything into Laplace domain, considering initial condition associated with all these energy storing elements are 0. So you will find for resistor it is Vs by V of S by R, for inductor it is V of S divided by Ls, and for that of capacitor it is Sc into V of S. Okay, so d by dt is replaced by S, integral dt is replaced by 1 upon S, and here you are having 10 by S because it is a constant function or unit step function kind of thing. Okay, then if you simplify this expression, you will find Vs is 20 divided by 1 micro S square plus S plus 2. Okay, so let us take this 1 micro here, and the simplified expression will now look this 20 into 10 to the power 6 divided by S square plus 1 mega S plus 2 mega. Okay, where m mega is 1 into 10 to the power 6. Okay, so if you find out the roots of this denominator expression, because you have to go for the partial fraction method, hence you will find S is minus 2.04 and S is the other value of the root is minus 0.98 into 10 to the power 6. So partial fraction method I have already done here for your ease, and you will find for S is equals to minus 0.98 into 10 to the power 6, the B value comes out to be minus 20, and if you substitute S is minus 2.04, the A value will come as plus 20. Okay, these are the approximate value. You will find 0.000 something, but that's immaterial, maybe you can neglect that, and hence the partial fraction will look like this. Now taking the inverse Laplace transform of the above equation, you will find Vt is minus 20, sorry, plus 20 e to the power minus 2.04 minus 20 e to the power minus 0.998 into 10 to the power 6 t. Okay, now from here also you can see, if you substitute t is equals to 0, this term will vanish to 1, this term will vanish to 1, and you can very well see 20 minus 20 is 0, and that's what we have analyzed in the first instance in the previous slide. D by dt of Vct at 0 plus, so what you have to do, you just differentiate it once and substitute t is equals to 0. So I did that for you. So differentiating it once means this 2.04 will come here in the front, multiplication with 20 will yield minus 40.8. Similarly, minus 9.998 10 to the power 6 will come in front here, multiplied with 20, it will yield 19.96 at 10 to the power 6, and this is 19.99 into 10 to the power 6 volts per second. Okay guys, please don't forget to mention this unit, that is very important when you are solving for such kind of examinations. And d2 Vct at 0 plus at dt2, the differentiation of this equation which you got in the previous step without substituting t is equals to 0. If you do so, you will find this value is minus 1.99 into 10 to the power 13 volt squares. So that's it for 2017 guys. Now we'll go for 2018 paper, okay, and then 2019. Then we will shift to some other subject, maybe the digital or signal system, that I will tell you in the next presentation. Please give your comments in the comment box. Please like it, share it, such that it will give me a motivation to prepare for the rest of the subject. Thank you so much.